Hi, my name is Drew. This is my Lab 2 experiment on barg magnets. I investigated how a magnetic field of a barg magnet changed with distance and compared my results to the magnetic dipole model. On the slide, you can see the experimental setup. We used a smartphone magnetometer to measure the magnetic field, and the phone and magnet were aligned to reduce interference. The goal was to determine how the magnetic field changes with distance and estimate the magnet's magnetic moment. Okay. You can see the on-axis measurements collected at different distances from the magnet. Multiple trials were taken, averaged at each location to improve accuracy. As the distance decreased, the measured magnetic field increased. Okay. Next slide. We talk about, there's the graph, and then we use this to determine the relationship between magnetic field strength and distance. The slope of best fit was approximately negative 1.41, which represents the measured exponent in the power law relationship. This value can be compared to the theoretical dipole prediction. Okay, so an ideal magnetic dipole, the expected exponent is -3, but my measured value was approximately negative 1.41. This difference is likely due to measurements being taken close to the magnet as well as alignment and sensory uncertainties. These factors can make the magnetic field appear to decrease more slowly than predicted. Okay, this calculation was used to estimate the magnetic moment of the barg magnet using the experimental data and the on-axis dipole equation. I obtained a value of approximately 2.3 ampere meters squared. This value was then used in the computer model. Okay, here you can see the off-axis measurement collected during the second part of the experiment. After collecting Earth's magnetic field, the individual components were combined to calculate the net magnetic field magnitude. The measured off-axis field was approximately 20.99 microteslas. The next two slides are the picture of off-axis, on-axis. You see the approximately 45-degree related to the magnet, while the on-axis measurement was taken directly along the magnetic axis. Use the magnetic moment, estimate, and measure distance. The simulation predicted off-axis magnetic field of approximately 20.98. Experimental value again was 20.99. The close agreement between these values suggests that the dipole moment provides a reasonable prediction. Okay, here's the code. So these slides show the code. The code estimates the magnetic moment and applies the magnetic dipole field equation to calculate the magnetic field. I'll focus on the results rather than the programming details. This section is the calculations of the magnetic field at the 45-degree observation point. The final vector and its magnitude are computed and then compared to the experimental measurement. The resulting prediction is the value shown earlier. Okay, this slide explores two hypothetical situations. The setups were not aligned correctly. Earth's magnetic field could affect the measurements and alter the calculated exponent. If two identical magnets were combined, the field strength would increase and the overall dipole behavior would remain unchanged. In conclusion, the magnetic field decreases with distance. Although the measured exponent differs from the ideal dipole value, the magnetic moment was successfully estimated and the off-axis prediction closely matched the measured results. Overall, the experiment demonstrates the key features of magnetic dipole fields. Thank you so much for listening. I appreciate your time.